Okay, we are here in this IEEE CASS talks from Rio Grande do Sul State Chapter in South Brazil. We are really pleased to have today a talk being given by Professor Jorge Castro-Godínez. A few words on the speaker, who will be speaking on enabling the intelligent edge through approximate computing. So the focus of the talk is on approximate computing design techniques. Professor Jorge Castro-Godínez is currently an associate professor at the School of Electronics Engineering in Costa Rica at the Technology Institute, Institute of Technology, TEC, is also known by its acronym TEC, is the Technological Institute of Costa Rica. He received his engineering and master degrees in electronics from the same institute, Tech Institute, in 2011 and 2014, respectively. And he did his PhD in Karlsruhe Institute of Technology, and he worked on approximate computing techniques. He got his PhD in 2020. And after that, he joined back his institute. Jorge's primary research interests are in the energy efficient computing across different abstraction levels of the design. So, with a particular interest on approximate computing and machine learning, applications, on edge computing devices. So, with not much further ado, let me thank you, Professor Jorge, for accepting the invitation of the chapter of the Rio Grande do Sul chapter of IEEE CASS to delivering his talk. I'm very certain and very sure that you will enjoy his talk on this technique, that is very state of the art and very important. So thank you very much for being here, Professor Jorge, and now the floor is yours for your presentation through this webinar.
Thank you very much, Sergio. Thank you very much, Ricardo, also for inviting me for this presentation. I'm really honored and flattered to have the chance to share a little bit of what we have been trying to do since my PhD, some ideas that came during that time and that I have continued working with very enthusiastic and brilliant students that I have the luck to work with. And also, this is part of the presentation I had a chance to give last November during the CASS workshop there in Porto Alegre. Actually, it was a very nice opportunity for me to get to know that beautiful part of Brazil. So yeah, I'm really happy to be here and have the chance to share with you a little bit of the work we are doing. So just pretty quick, and this I normally do it as a joke for folks of other parts of the world, and it's about if Costa Rica is an island, because sometimes the word Costa Rica and Puerto Rico sounds pretty similar to many, but we're not an island. So we're in the middle of the Americas, connecting the two big chunks of North America and South America. And just for reference, and this was some data I gathered when given this presentation in Porto Alegre back then, is that in terms of population, just the state of Rio Grande do Sul has twice the population and 5 times the area that Costa Rica. So we are a very, very small country. As Sergio was saying, I am part of the faculty of the Electronics Engineering School here in Costa Rica Institute of Technology. So this is an overview of our campus, and here in red, I'm just circling our building where my office is actually located. So Costa Rica Institute of Technology, it's one of the leading technical institutions here in Costa Rica, alongside to the University of Costa Rica. And even though we are a small country with not so long tradition in higher education, like for instance in Brazil, we have a growing industry. And this is something I normally try to mention because in a way I'm proud of my people and the talent that we have here, and that we have over basically the last 2 decades being able to attract very interesting companies to the country and then provide very interesting positions for many of our students. So from the microelectronics perspective, and going across all the different abstraction layer. So we have very interesting companies working here in Costa Rica, such as Intel, HPE, Siemens EDA. Probably many of you have the chance to listen to the presentation by my colleague Alfonso Chacon some weeks ago regarding their own company called RIDEV. So there are many different, from the manufacturing perspective to the design to the verification, from the, as I was saying, from the perspective of CASS topics, but also we have like many interesting companies also doing interesting jobs here, like Microsoft or Amazon, not only providing services but actually doing development. Um, from high-end software to low-end software, more focused to embedded systems and so on. So this is something I'm kind of proud of my country and the talent of the people that we have here that has provided a good scenario to these companies to come here and stay. So this is just a little bit about my country and myself, but I always like to talking about approximate computing to come to like the motivation that has in a way um, opened the possibility to this paradigm. So, and the question is how we got here, how we got to the point in which we want to, and we're going to be talking about that more in some minutes, to reduce the precision, which is the main idea of approximate computing, to reduce the quality of the results in order to gain a different levels, to gain an energy level, to gain an area size of a circuit, of execution time. So we have experienced in the last 2 decades different important effects. One of them, it's knowing that Dennard scaling no longer really applies as we go more into the submicron and the nanoscales of the transistors. There is an inflection point in the middle of the 2000s that actually make the industry to switch from just big processors to then have multiple processors working probably a lower characteristics, but then introducing the need to change the way that we are developing our software to then take advantage of multiple cores and all the challenges that are related. Also, Moore's law, still people believe it's still applicable in part, with this switch that we are having and seeing in the industry from a single die to multiple dies into a chiplet technology. So is it coming to an end? It's really helping, or are we going to be able to actually keep scaling the devices or not? And these in the early 2010s, something like that, um, uh, show more particularly as an utilization wall. Yes, we have tons of transistors, tons of silicon right now, but probably we cannot use it uh, at the same time. And this is a very challenging problem that it was coined as dark silicon in the past, that has bring to the research floor the questions of, okay, how can we better use this silicon that we have available to increase performance, but try to do it in a way that we are not burning our chips because of thermal issues or power issues. This is one of the I will say lines that we need to consider, the different physical phenomenons that are making or introducing challenges in the way that we do computing. But on the other hand, we have the type of applications that we are trying to target. For all of you, for sure, it's not a surprise, all the advancements that we have seen basically in the last decade, in the last 5 years, and in every week and every month we see, I would say, crazier things in the scenario of artificial intelligence and machine learning. But then there is one particular issue, and that doesn't come for free. They require hardware for having such big models to be trained and then to use them for execution are pretty large, and then the carbon footprint that this represent is something that it's indeed very terrible. So this was very surprising for me when I read it and learned about it. And this is already like old data, I would say, but just one particular NLP model could take for his training, or could produce for his training, 5 times a carbon footprint that a regular average car, fuel car in his lifetime. So this is pretty amazing in terms of the numbers, but also very concerning that the way that we do compute, it's actually affecting the the nature in different ways, because we are consuming too much energy, we're producing too much carbon that probably we cannot fix, and this is a very issue. So question is, how much carbon footprint, for instance, something like GPT-4, which is still new but all at the same time, could require for just doing a training. And nowadays, probably what we will like to consider, and always, it's, increased performance in the computing that we do, but now with a more with a higher conscious of how much watts are we spending, and then how this is translated to this carbon impact in the environment that we're doing by performing computing. And this article by Rob Aiken, I think it was a very good way to, in my personal point of view, to have this into a more clear consideration. It's not something new. It's not that in the research we are not considering how we can increase performance, but reducing the amount of watts that we have, but probably having this as our new Moore's law, focusing more into this. And we see across the industries how different technologies are more focused into the application, and then increasing the performance while being more considered regarding the power consumption has been introduced. So I always tell my students, we came from the compute systems that were application specific, to come to something very generic that we try to use for kill every problem. But now we're moving back to the days where we need more specialization, that we see pretty heterogeneous systems, in order to try to increase this sort of performance while reducing watt consumption. This is probably a second bucket I wanted to mention. From one side, the physical challenges that we're experiencing in technology, the type of applications we're having. And then another important aspect is that in all that we do, we don't necessarily need to have a full precision, or we need to always have the best result, because probably having just a good enough result could serve pretty well for the purpose of the application that we have. And by compromising that, we can then have significant savings in the way that we do computing. By just reading something not non-technical at all, I was amazed. I found this aspect of or this term called satisfying, that it was coined by Herbert Simon, which was a Nobel Prize in economics. So probably if one of us needs to get a pen just for writing some notes, some research notes, or just take notes of meetings, and can get to a bookstore, could find like many different types of pens, but probably most of them will work fine for what you need to do, which is just writing. And not necessarily you need to run a benchmark to find what is the very best pen that you can get with the best way to provide an ink that will last a little longer and is the cheapest. You just need to take one, and it's going to probably satisfy you. So this idea of satisfying, as described here, is probably not necessarily getting the best option, but just getting a good enough will be fine enough for what you need. And then finding probably an equilibrium between the effort, in this case, from our perspective, the computing resources that you need to put in, and the benefit, the quality of the results that you get. You can then probably find this sort of trade-off to reduce the benefit you get, the quality of results, but then also have significant savings in the effort that you need to put in. Sometimes we think also that the more there is, the better it is, but not necessarily. And also, by also reading something else, got my attention. Sometimes we get pretty focused into technical domains that other ideas that have been already explored can provide light that probably we're not aware. And this law of diminishing returns also got my attention a couple of years ago, in which many systems, many processes, just putting more resources probably won't give you a larger benefit, and you might find yourself in a point into more resources will have no effect at all, and then it's the point of maximum yield. It's up all you can get for the resources that you are putting into. So investing more not necessarily will get you to a better result, and Similarly, you can just reduce the number of resources that you're putting and still being able to get good enough results. Meaning that, and from the perspective of approximate computing, we can find some compromise in that sense. And then, lastly, just to motivate this, is it's this quote from Robert Reed, that it's better to be vaguely right than exactly wrong. So yeah, sometimes we better have a result that it's pretty close to what we need, but we can get it pretty fast and with less effort than then go all the way to the process and then get something that it's totally wrong and it's useless. So with this three different buckets, I wanted to motivate my talk regarding what approximate computing is, and to show you from my perspective, from the work I have been doing with, as I was saying, very enthusiastic and brilliant students, at different levels, what we're trying to achieve with this technique. But just to put ourselves into the same page, let's define in a way approximate computing. So we know, and I was motivating about that, power and energy are design concerns in modern computing. And from the other hand, many of the applications, many of these trending applications and workloads that we're working on right now, that we find in every time in more and more devices, turns out that they have some sort of tolerance to the errors. And then approximate computing, as a novel technique, what it aims is to try to find a way to design systems in general, from software to hardware, in an energy and efficient way, by trying to exploit this error tolerance of the applications, and then, as I was mentioning, just lowering the resources that you need to put into and getting results that are still good enough. So in general, we're trying to reduce the quality, whatever that we call the quality to be, probably just the accuracy of the results that we get. And by doing so, then we reduce, for instance, execution time if we're applying a technique at the software level, or if we're designing a circuit, then probably reduce the area and hence, for instance, the power. And by doing so, what we're trying to achieve is that we know we're going to get less quality of the results. The less quality that we can still tolerate and that we can compromise, then the more the savings that we can get, right? And particularly, and this has been motivated since basically 10 years in the literature, it's that many of these applications present certain characteristics that make them a good candidate for then compromising this precision. So, for instance, this can be, in many cases, compromises because not necessarily the application has a golden output. We might be seeing some application that performs some sort of classification, and at the end, what we get is a percentage that, well, this that we are showing to, for instance, a neural network might fit into one or of many categories with certain assurance percentage regarding that, and then we can still lower that estimation and still, be selecting that category or characteristic from the output still correctly. In many cases, for instance, if what we are doing it's some sort of image processing, there are some natural perceptual limitations that you and I as human have. But in many other applications, probably we have redundant input, or just by nature, there is a lot of noisy data that, yeah, we can still, work with that and not need to necessarily clean it to still produce good enough results. And from different state-of-the-art works, they have shown that the percentage of the runtime in many applications for particular kernels that are taking the most of the time, for instance, like having a dot product or calculate an Euclidean distance or having some matrix vector multiplication, they take most of the time, and turns out that these sort of application or computations turn to be error tolerant. So there is a large percentage to have an impact if we can have some way to still calculate these kernels, but reducing the resources that are requiring. How much can I relax my computations? Well, this is always a question I get, or how much is good enough results for having an application or applying to an application, an approximate computing technique. Well, this is gonna for sure depends on the application. It's not that we have necessarily a unique way to say, okay, this is how much you need to or that you can tolerate, but it's going to be on application base, and it's going to depend on what are the final accuracy and quality requirements that you have, to then take that as a starting point and see how much you can squeeze your design, or you can cut some corners into your implementation to still produce a good enough result, but then reducing as much as possible the resources required. Also, the question is the critical section the one that it's taken most of the time of the execution, the one that is ever tolerant? And probably you have heard about this idea of the 80-20 rule, that probably, like, let's say in some code application, 20% of the lines of your code consume the 80% of the time of the execution time. So can we actually have some margin of exploration for this 20% of the code that will have a larger impact? Um, can I tolerate some sort of deterministic or non-deterministic errors? Meaning, for instance, for the same input, I always get the same error, or no? Probably I will get some different errors because probably what I'm playing around is with the supply voltage of the chip, that will probably make it a little bit more non-deterministic, the error type. What do we care about? Energy, runtime of data density. These all these aspects, all these questions have a role into this play to then defining, okay, what are the techniques that are available, what is my application, and how can I apply them? And for sure, one very important aspect that in the community it's pretty clear, it's that we want to approximate the way that we process the data, but we don't want to touch the control, because if we change the control of an application or what we have in a circuit, probably I don't want to touch like the finest state machine over my circuit, but I want to touch the way that the computations of the different data it's being performed, because I want to keep the correctness of the application, although the results are going to be produced will be up to a level compromise. And another thing coming from the motivation of this talk, which is edge computing, is that many of the devices that we have on the edge of the computing spectrum are required to be generating tons of data. And it's well known that cloud computing it poses a lot of challenges, from data privacy to reliability to network latency. And we would like to have the computation where the data is actually being generated, because just moving, and this is an estimation I found for autonomous vehicles, and the plethora of sensors and computations that need to do, could be considered that up to 19 terabytes per hour can be produced from this sort of vehicles. So it's a massively large amount of data that we need to think that it's going to be, if we don't compute it, if we don't process it there, need to be uploaded somewhere to be processed. So of course, this is totally unfeasible. So yeah, this is also part of what we want to have. And from the industry and academia, the idea of this intelligent edge, of having something or having the possibility to have the devices that are at the edge of the computing spectrum with the capacity to actually process the data in a smart way, an intelligent way, meaning, well, applying probably artificial intelligence or machine learning algorithms to this data that's generated, becomes a new challenge, right? We cannot run the large language models that we have access to today, probably in a device that is such as constrained as an embedded device. But then it becomes a challenge: which parts we can move to the edge, how we can make possible to, let's say, squeeze in these applications in order to still have the possibility to run it into very constrained devices. And more recently, like the past 3-4 years, I have been working on different ideas that try to aim into this direction, right? How we can make possible to have these complex applications into this sort of devices. And I want to summarize for the rest of the talk different of the contributions that we have been working on, mentioning, of course, what are the types of techniques from the approximate computing domain that we are trying to apply. And I would like to finish a little bit with some perspective that we presented last year in the approximate computing workshop, which, and by the way, I make a small announcement. We are, or I am, together with two very brilliant colleagues from Italy, organizing this year's workshop that is going to be collocated. That's our hub with ICCAT. But I want to finish in that sense, presenting some ideas that I think are still open to the community to actually enable in a larger scale these different techniques, and especially thinking in this type of applications on the edge. So the first one I want to talk a little bit, it's about approximate logic synthesis for traditional machine learning algorithms. So to put into context, many of you already know the logic synthesis process, from taking an RTL description and then having a lower level representation of it down to a GSD2 if you want to manufacture your own chip, right? From the approximate computing perspective, the idea is, okay, let's have in between the process a way to generate an approximate circuit from an accurate implementation. And in the community, different ideas have been proposed, mainly for simplifying this function from netlist transformation down to approximate logic synthesis, which, it's basically taking the approximate logics, the high-level synthesis flow, to then introduce different approximations at different stages. That's part of what I mainly worked during my PhD. Or could it be also by leveraging an existing high-level synthesis and then feeding it into a specific way to still generate a circuit that it's going to be good enough? And I'm going to be commenting a little bit about the second approach that we have been working on. But also, in this case, from the netlist transformation, you can imagine that you have then your representation of your circuit, and then you can decide which parts of that circuit you can just prune, you can just remove, and still be able to generate good enough results. One challenge we found when trying to start working on that domain of approximate logic synthesis was the missing of an open source framework to actually introduce your techniques or test existing techniques from the state of the art and be able to compare against to whatever you're trying to implement. So we came out, and it was still part of my PhD work, some tool to actually, in having like the traditional synthesis flow, take the netlist representation of your circuit, and based on the technological library that you're using, try to have a representation that can be, let's call it, easier to manipulate. So back then, the decision we took is to have the representation of the netlist as an XML file, but with the possibility that, once you synthesize your circuit, have a representation according and knowing also according to the tech library what you have there. And by having then this, be able to introduce the different techniques that from a state of the art have been proposed to modify the circuit and then generate an approximate one. Of course, this requires that you introduce some sort of approximation criteria. This could be, for instance, the commutation probability of the gates, or could it be the position and the influence of a particular gate to a particular primary output, or or you just want to cut a primary input and then all the affecting part of the circuit, try to remove it in order to gain area, for instance. So in this tool, what we were able to do was to have a way to manipulate the netlist, generate an approximate one, and from that perform different simulations according to to the techniques, how often we will need it. In this case, to be able to estimate what is the error that is being introduced to the approximation criteria, that it's expected to be working up to a level, up to an accuracy threshold to stop and then generate this approximate circuit. So, and just to provide some sort of idea, like for a 4-bit adder, like ripple carry 1, or 2 could be for one particular technique, in this case probabilistic pruning, try to define, okay, which gates I need to prune, I need to reconnect in some cases some inputs that are now missing to some particular gates, and then be able to still produce errors that are good enough. So for this case, for instance, the larger error with a lower probability, in this case, it's going to be 6. So defining, for instance, how large you want to have an error, and for a particular technique, then let the technique define what is going to be the resulting circuit, cutting some of the different parts and rewiring in some cases to still produce good enough results. Back then, just for the sake of the tool, we did an evaluation pretty similar to other works in the state of the art. For instance, having like 16-bit adders or 8 to 8 multipliers, things like that. Pretty simple. But then this idea was taken by Bruno Abreu, that probably many of you know there in the south of Brazil, to then let's use this technique or this possibility to apply different techniques to cut different parts of the circuit and apply it to tree-based and machine learning accelerators. So Bruno was working back then on decision trees and random forests, and then create a tool, a very interesting tool, to perform the translation from the tree description to an HDL implementation. And then by taking this HDL implementation and then feeding it to our tool, to the AXLS, have the chance to then start cutting some of the different parts of the circuit to look for the possibility to still generate a resultant circuit that will provide very high accurate results, while, for instance, reducing significantly the energy consumption. So in this case, and for this great work that Bruno did, taking his work on generating trees and our work for this tool to generate these approximate versions, we were able to see that for many of the cases, even for different tree depths, that of course the larger could produce higher and higher accurate results, still for most of the cases was pretty I would say horizontal, to see that in this case for the 3 applications we were benchmarking, that reducing the precision, or reducing the circuit, which is here reflected by the error savings that we were achieving, we were able to still to get results that were maintaining basically the same accuracy, or it was just dropping a little bit. And even though, of course, the hype right now, it's large language models, there are still many applications that can be solved with traditional machine learning implementations. And in this case, thinking in this sort of wearable devices, where we want to really reduce the energy consumption to extend the battery as much as possible, at least we were able to see that, yes, it's possible to generate, in this case, the circuits representing the applications in which still we can compromise the accuracy for a little bit, but get very large savings, up to 50-60%, depending on the application, and depending, of course, on the tree depth, without really losing any significant accuracy. So this was a very good way to integrate to different works, and to show the benefits that we can get from approximate computing. More recently, we have continued a little bit on this idea, and actually together with Guilherme Paim, that also I'm pretty sure many of you know, we were discussing someday ideas, and we came with this naive idea to probably reuse the synthesis as part of the approximate logic synthesis steps. So normally what we were doing is just generating a single logic synthesis and then just relying on the pruning technique to start cutting gates, start rewiring, let's say, and then generating results. But probably by considering the resynthesis, basically, once we do some pruning step, just tell the logic synthesis, hey, we have this, try to optimize it, let me get whatever you can a round of pruning technique. We were hypothesizing that, yeah, probably we can get better results. We can reduce the design space to explore, and by doing that, of course, get the results in a larger and in a faster way. Because many of the challenges on these net list transformation techniques that have been presented in the community, it's that the larger the circuit is, of course, the larger the design space becomes, and then the execution time for performing this exploration grows significantly. So in many cases, not necessarily converging in a reasonable time. So This was one, as I say, naive idea that we start playing with, and I had the luck to have a very good student that took this idea, introduced many more techniques into the tool, into the AXLS, integrate completely the open lane flow. Before we were still relying on proprietary tools, which is fine, but we wanted to be able to provide our entire tool as an open source contribution, leveraging on all the open lane flow. And what it was interesting to see is that yes, for different techniques, of course, different circuits, still we were testing similar circuits as we see in the state of the art. We were able to get a faster savings for probably no degradation. For instance, in this case, by also taking one of these decision trees from Bruno and trying to apply this resynthesis, we were able to see that in shorter steps, we were able to reduce more significantly, for instance, the area power product, while basically not degrading as much of the accuracy, or in this case, represented as error rate, but also we saw different results in along these lines for these applications and for the different techniques that we were testing this resynthesis idea to. Luckily, this is a work that we hope soon it's going to be published by IEEE Embedded System Letters. It's already accepted. But this is just from the results of the circuit's perspective, but also from the execution time, that it was the other hypothesis that we had. We actually saw that even for some larger or the larger case, we were able to even save up to 30 times the required time for just performing the exploration, that just relying on the technique was taken in consideration, that having the technique, but having resynthesis steps along the way. So I think that still for many different applications that, we really need them to be very low power consumption, having this sort of ideas can still produce very interesting results. Another thing, and this is from, and the previous one was from the basically hardware design, but moving a little bit into probably software perspective. Also, one of the things that I was interested to explore is, okay, we have off-the-shelf devices. Of course, we cannot modify too much the hardware, but let's figure out what we can do at the software level. What type of techniques at the software level can we really introduce to improve performance, and especially how we can combine different techniques to even have larger savings. So Tomas was a master student of mine, did a very interesting exploration, having in this case as a base platform some Raspberry Pi 4 with this neural compute stick from Intel. Back then they were still selling these devices. So we were leveraging this sort of neural processor to perform the actual inference process, the high part, in particular for three applications that we tried back then. Some audio classifications, some fruits, and some scenes classifications. We were able to see something very interesting. And this I'm highlighting the best results we got, that particularly were for the case of the scene classification. And in part, we saw these good results because of the large set of parameters that we were having, especially for that case, and the larger the images that we were processing. So we saw better the effects of the techniques in this larger case from the three of them. But from a base implementation, that it was already improving the performance in 20x. So just by executing, in this case, a scene classification in the Raspberry Pi 4, and in comparison, executing that together with this Mirad X, which is the name of the chip in this neural stick platform, just that baseline was helping us to get 20x improvement in performance. But then we started looking, okay, what type of techniques we can do? Can we do some sort of reduction of the data of the input set? We can reduce the layer size. Can we do some sort of pruning? Can we do some combinations of them? So we came out to a point, or one of the combinations, in which we were able, from this baseline implementation, to double basically the performance, meaning that from the actual baseline that was executing in the Raspberry Pi to go to 40 times improvement in this case of the performance of the number of images that we were able to process per unit of time, and still also having an improvement in the power and the consumption, meaning that we were improving the metric of performance over watt on that sense. So this was a very interesting exploration that Tomas helped me to do, to realize that yes, we can still find techniques that isolated can help. If you see the different techniques here isolated, we're able in some cases to produce similar or better results as the baseline, but then having the right combination of them can still maximize the savings that we can get. Moving forward, we're trying to automate the process and the exploration of these techniques. So I have another master student already working on this. We're now trying to aim this edge TPU from Google. There are some specific platforms called some Coral AI, and nowadays we're trying to expand this work to a larger benchmark. In this case, trying to use the standard MLPerf. Bringing also these software techniques and trying to find a synergistically way to apply them, but also that to have some sort of design automation in the sense of the exploration itself of the techniques that can be applied. Something in between, probably, from hardware design to software implementation. It's how can we have, for instance, high-level synthesis models that are meant for implementing DNAs and FPGAs. So this was also a question I had from long time ago. How can we really leverage FPGAs in that sense, and also taking into consideration this idea of the intelligent edge? It is expected that FPGAs are going to be key players, particularly because they are in a good trade-off between the flexibility they present, the power efficiency they have, and the performance that you can get. So yeah, it's expected that for sure any sort of deep learning application, especially if it requires some sort of tailoring and reconfigurability on the field, that will rely on FPGAs. So long time ago, with a very good master student, and now is a PhD student, it's almost finishing, we started looking at how we can leverage, in this case, standard out-of-the-box high-level synthesis tools to try to generate, and of course, by trying to generate in just using the tool with all modifications, relies more in the way that we provide the information to the tool, in this case, the way that we describe the model, which at the end, it's going to be a C model, C++ model, but it still will require a way that we tell, okay, we want to have this computation in this way. And by leveraging, of course, the different, let's say, knobs that the tools provide to then have different generated circuits, we were able to start looking into deep learning and image processing applications and try to see, okay, where we can find a trade-off. For instance, some of the ideas we have been exploring, it's okay, we don't need all the same numerical precision, probably not necessarily a power of 2 precision. We can go to something more tailored to specifically go for the application. By doing so, it's that we have been able to really see good savings in terms of the required lookup tables, for instance, that at the end are required for the implementation. Also, by changing the arithmetic operators, this has been broadly explored in the community by having different ways to do the computation. But also the challenge here is, okay, how we do it in an FPGA, because not necessarily the techniques that we have for regular circuits apply exactly for the FPGAs. In trying to build from the ground up a library of different approximate components, in this case, for instance, matrix multiplications, based on different algorithms from standard to Strassen to Winograd, to then be able to come with a way to map applications using these components from this flexible accelerators library, and then be able to tailor the application up to the requirements that we have. So Luis has been able to introduce even some design space exploration into it, and being able to provide the different components that needs to be put into the different boxes to actually generate accelerators, in which we are leveraging on approximations, approximate computings, for instance, just by reducing the data representation or the matrix sizes that are actually compute, and then have interesting results. Actually, most of them have been already published, and some particularly in ACM text. And I wanted just to show, for instance, that from this perspective, by integrating, as I was saying, different matrix sizes, data representations, different approximate ways to do the operations itself, and having this design space exploration already in place, integrated. Now we are able to do this sort of explorations, even before trying to deploy something in an FPGA. So this is a case for a LANet 5, as I was saying, for different approximations within the layers. And it's pretty useful. Of course, it's still time consuming. That's part of what Luis has been also working on to improve the velocity of the DSC. But in this case, we can see that we can play around with different design points and still find good Pareto optimal solutions for the different scenarios that we have been playing with. This work from Luis has been also in a way increased to came with something that probably many of you are familiar. And actually the barrier for actually using FPGAs, it's pretty large, especially for people coming from the software domain. And similar to PINQ or PINQ, which is some sort of layer introduced by Xilinx to then leverage Python descriptions to then are going to go down and run into a mixture of FPGA and hardened logic. Since Luis has been working exhaustively with C++, in this case, for generating this library, this SyncQ idea has come. So similar to PINQ is to have all the flexibility from PINQ to have your models and be able to deploy it into an FPGA, but with the advantages of having, let's say, a C++ or a higher performance in comparison with Python. And for some work that has been already submitted and we are waiting the revision, one of the important things and the highlights of this is that by using Sync or SyncQ in this case, we can get faster results for different implementations, from image filtering to in this case a multi-layer perceptron implementation, while at the same time reducing the required time to generate the different artifacts or the required size that you need for storing your stuff in your machine. One important aspect of bringing the intelligent edge or having an intelligent edge is that DNA's implementations are vulnerable to some sort of attacks. In this case, adversarial attacks have been widely explored and reported in the literature. And one of the questions that we have had, not yet are we there into the implementations into FPGAs. We're still in the model evaluation process, but it's okay. Once we have one of these DNAs implemented in an FPGA, how vulnerable it's going to be, and how the approximations that we are introducing can even help to reduce this vulnerability and actually increase the robustness. So in a nutshell, this idea of adversarial attacks is basically that the inputs can be perturbated, noise can be introduced, and by doing so, a pre-trained model cannot generate probably in the same way some sort of classification, like in this case, misclassifying some sort of traffic signal. One good thing, it's in the literature already have been, or there are contributions to perform this sort of approximations, explorations into DNNs, having a DNN model, get to know what it's the effect of introducing, for instance, approximations into a multiplier. So we have leverage of this tool called ADAPT that was created also in part from a colleague of mine. And we are starting to introduce to pre-trained models approximations itself, but also introducing these adversarial attacks to try to look, okay, what's going to be the effect? If we introduce approximations, of course, we expect that without an attack, we're going to degrade the accuracy that we have in. But once the attacks start appearing and and the perturbation budget start increasing, what's going to be effect? Can we become a little bit more robust against this? And the preliminary results, this is also a master student that it's working with me. It's finding it's a yes, actually in most of the cases, of course, we are not, radically changing the accuracy and keeping the accuracy to 100% from the baseline when the attacks are introduced. But we are seeing that we can, move the robust accuracy higher, still, and even with the perturbation budget for different attacks that we have been exploring so far. And for different applications, like here I'm showing for Landed 5, ResNet 50, and VGG 19, we are able to then have this robustness improvement. We're still in the process of exploring, for larger nets and for newer attacks, and particularly also to deploying this type of implementations then into an FPGA, into hardware, and then getting to know, okay, what is the actual impact that this is going to have. And another way, probably just moving around, I have shown that, well, using different approximate computing techniques, we can improve, let's say, the area required if we're implementing something in an FPGA, or in this case, improve the robustness if there is an adversarial attack. Another work I contributed with is, okay, probably we can have the actual approximations using an artificial neural network. It's well known that neural networks are by nature non-exactly, or are non-exact, are not going to produce an exact result. And the main idea is, okay, if I have a heterogeneous system and I have to put like different approximate versions for one or different applications, probably there is a way in which I can find a good compromise, because of course having a neural network implemented in hardware requires a large amount of resources, but still I can generate, or I can leverage the neural network to produce approximate results. And this is a very great collaboration I did with Benjamin Karen Schaefer, professor in the University of Texas at Dallas, and his PhD student, in which we were looking, okay, probably we can have for specific approximate accelerators some part map into a neural network, but then probably we can find a way to combine the usage of a single neural network to be used for multiple accelerators. The work Protai, PhD student back then, did was pretty amazing in terms of implementation perspective. And at the end, we were able to perform evaluations in which we have a whole system, in this case implemented and leveraging some high-level synthesis tool, in this case next tool called Cyber Workbench, and have different combinations of approximate or in this case accurate accelerators that then will convert into approximate ones, and in which a single artificial neural network was used to then produce a part of the results. And we were able to find very interesting results for, fixing, of course, the maximum error that we wanted to achieve. We were able to see, how area and how power was reducing as per the proposed method of sharing, in this case, an artificial neural network. So in that sense, also, when we are aiming not only to move into this resource constraints devices, also these sort of approximations can also help. And I want to finish in the minutes I have left with a little bit of my perspective regarding approximate computing, and especially when we think on complex applications being deployed on this type of systems that are pretty resource constrained. We need to think, at the different layers, how we can leverage to then improve the savings that we have, increase them, but still produce very, very good results. I very like this image that I show here at the right. I always, basically, since a couple of years, I share it with my students at the beginning of the classes of the semesters, to show that for me this is the real full stack development, from application software down to the physics. So trying to exploit different techniques at the different abstraction levels is a challenge. It's still not fully addressed in the approximate computing community. And yes, we have very good results applying one technique here, software level, as I was showing, for for this out of the box platform that we were using with the Raspberry Pi and this accelerator, or probably at the digital circuits as we were introducing approximate logic synthesis techniques. But we are not yet there in the process of really integrating, combining in an aggregated way these techniques to maximize, as I was saying, the savings that we can get. And for me, there is still a need of synergistically use of the different approximate computing techniques that have been introduced at the different abstraction layers to then really maximize the savings. Not an easy challenge, but I think it's still at the maturity level that the community of approximate computing is, probably is a natural step to move forward. So there are different aspects that are a challenge still, and this is part of what I wanted to show or to write or to comment to you at this right moment. One is this gap between accuracy and quality, probably for the type of applications I was showing. Quality at end, the classification accuracy, if it is for the application or the error rate, will be the final metric I want. But depending on the application itself, the metric is not necessarily the same. So we don't have a metric to rule them all. So this is still required from my perspective, to develop top-down methodologies to bridge these quality requirements down to the specific layers, to then tell, okay, what is the accuracy that I expect for each layer, that then in the aggregation of the different approximations to be able to meet whatever I'm expecting as an output. Even, and this is something that has been already explored in the community, it's that applying different techniques at different abstraction layers can even help in a way to mitigate, not necessarily amplify, but mitigate, attenuate the different errors, making that even though you have in between approximations, those can be, let's say, self-healed, and then at the output you can get the quality or the accuracy at the output that you're expecting. So still, finding a way to map this quality or desired quality down to the different layers to define what its accuracy require is something missing. The other thing is that you need to find the right approximation at the right level. So we don't have a silver bullet technique right now. So we need to find, what are the techniques that are right for each layer, and especially when we try to bring them together. As I was saying, it's important because then errors generated by one technique at one layer can be amplified or attenuated. We want to attenuate it in this case by another, accurate or approximate computation that can be found in another layer. So then, identifying exactly which are the right techniques, and then the interaction between techniques among layers, it's crucial, aiming to these cross-layer system level optimizations. And last is also try to find a way to perform cross-layer error estimations. This is not a very easy point, because as we are applying different techniques at different layers, we want to, without just running into exhaustive simulations and software executions, to find out what it's going to be the accuracy degradation. So, and this is very important to reduce these different gaps into applying different techniques. Each technique already has error estimations and so on. Very likely, I did some work on that sense during my PhD, but then integrating it into different layers, as I said, it's going to be still a hard problem for us to solve. But still, I think from the approximate computing community perspective, there is tons of works that can be done, especially when we think in these applications, when we think we want to enable the intelligent edge, in which we might have systems in which we can tweak, hardware, software, combination of both to maximize the savings, to find the right accuracy that we will need, and then from that point of view, just reduce as much as possible the resources that are required. And also, as I was saying, trying to improve the robustness when considering, the reliability in that sense of the executions that we have, since we're going to be expecting to have these computations where the data it's actually being generated. So yeah, this is part of what I have been working and thinking about regarding approximate computing probably in the past 3 years since I finished my PhD. And for me, I'm so glad to have the chance to share it with you, and I'm totally open to probably answer some of the questions. And please feel free, if your questions are not answered at this moment, to reach out, and I'll be happy to follow up with you.
Okay, thank you, Jorge, for your very interesting talk. We have two questions here in the interactive channel of the IEEE CASS chapter. One first question is coming from Luis Leon Vega. I think he is your collaborator in Costa Rica, probably. He's asking if it's possible, since we are worsening the quality, that we also affect the robustness and introduce failures in the circuit. Is that possible? And he wonders how it will affect the system in terms of security.
Yep, this is a very good question. Actually, some folks in Paderborn University in Germany are now having these questions and trying to, address these issues, because it's not yet totally clear. For sure, we are weakening in a way the circuit. We are aiming right now. It's just to reduce the resources that we need, but at the same time, we might be opening some doors to some security issues. And this is something that is still the community, I will say, hasn't fully answered, and this is a work in progress that I'm aware in different research groups. It's a possibility. Then it's the matter of trying to find, how much approximation can I introduce without not only affecting, for instance, in this case, security, but also if I have into consideration what I was also mentioning regarding the robustness, how can I also mitigate the impact of adversarial attacks? If both are, my concerns, can I actually at the end of the day apply approximations and still, not open any security door, but still cover myself into, or protect myself to a certain extent for these adversarial attacks? So these are still open questions. For sure, security is a concern to a large portion of the community in general, circuits and systems, when considering approximations into it. For instance, in the terms of reliability, it has been also demonstrated that for some applications where you normally need to expend a lot of redundancy, double, triple redundancy, even approximate computing can be used, reduce the resources required, and still be able to produce, let's say, secure results in systems or type of systems when you need to have this sort of redundancy for safety. This is still an open question for sure, and I'm looking forward that
Okay.
groups to really have good works in that direction. Yeah.
Okay. There's another question that I wanted to address is about the high-level synthesis results that you use. So exploiting approximate computing at the high-level synthesis with high-level synthesis tools opens up a huge design space.
Right.
So from the results that you have shown using that for FPGA, can you ask first, have you used Vivado HLS for those results, or have you used a more general tool for HLS? And what's your feeling about that? Because I think I may have a point regarding that high-level synthesis will not lead you to the best, let's say, Pareto point, because it has an open, let's say, RTL space to map to. So what's your experience and your thoughts on this?
Yep. No, this is a good question. Actually, from the HLS perspective, my first works were more into, okay, let's have a tool. You need the high-level synthesis tool, and let's try to find a way inside the tool to introduce the approximations. This is normally a challenge because most of the tools are commercial, they're closed source. Back then, I was lucky to still use one. Nowadays, I don't know exactly the name, but back then it was called LegUp, and it was still
it's a University of Toronto tool, yeah.
Yes. But then it was acquired by Microsemi, I think. Now it's part of Microchip and so on. So having a closed source tool, the problem is, yes, the degrees of freedom to actually manipulate how the tool it's generating the circuit, it's more constrained. You don't have that freedom. So you need to rely into, the parameters that you can modify through pragmas, for instance, to have the different versions of the circuit that you can generate. That's one of the points. But the other, it's okay, how we feed this from the model perspective, because at the end you are using just C, C++ to model whatever you want to map. Ideally, it's going to be a one-to-one translation from whatever you have actually running into a processor and you map it. Many of the times it's not the case. You need to do modifications because it's required by the tool. But yes, from our experience perspective, the way that we provide this, the way that we tweak, for instance, the precision of the data, how many bits we want to have for the exponent part, for the mantissa, and so on and so forth. It's a key aspect to actually use the tool to then generate something that now it's not going to be accurate by design, and still be able to explore, as you were saying. Yes, the design space grows exponentially. It's not an easy task afterwards.
If you allow me to make a point, if I were to explore the HLS, first I would do the precise architecture and do the exploration at the precise level. And once I'm comfortable with the, let's say, the trade-off between PPA, performance, power and area, then I would take that HDL that generated by HLS and then apply more conventional approximate computing techniques. I think
Indeed,
you are more likely to get better results.
Indeed.
Okay, that in my advice to students and people listening to this talk.
Sure. No, for sure. Actually, for the lack of time, I didn't present the full extent of the work, but that's what we have been looking at. From one optimized, totally accurate implementation, let's have that as a starting point to explore approximations, because that it's going to be at the end of the day also application dependent. But this is the way, at least the works that we have been contributing to the community from this perspective, exploiting an standard high-level synthesis tool, which we're using. It's Vivado HLS so far, moving also to VT's HLS. It's basically that. Find what it's going to be, let's say, the Pareto optimal solution for the accurate implementation, and from that point onwards, introduce the approximations as much as we can have to then explore the design space. Yeah.
Okay. Well, thanks for the answer. And since we are in the HLS high-level synthesis field, there is a question by my dear friend and founder of the Circuit and System Activities in Porto Alegre, Professor Otamiro Suzin. Thanks for your question, Suzin. Thanks for being here. He's asking on the high-level synthesis strategy. He would like to know if you mean a single application exploration, or are you addressing adaptive hardware for inside the application? That's his question. Okay, it's still on the realm of how you did the HLS and what you mean by a single application, or do you mean an adaptive platform instead?
No, this is a good question. Thank you very much for it. So far, it's only one application, and the deployment of the or expected deployment of a single application, without necessarily considering some sort of reconfigurability, let's say on the field. Once you have the application, to do some changes. This is something still on our table, to consider, because then you're going to be facing some different issues. Which part can you really replace? If you need to then change entirely the application or the implementation for the application itself, how much time this is going to consume, and there are different aspects that you need to consider. For sure, having some sort of architecture where you might have a standard base, and if you can then reconfigure to adapt to different accuracy changes, over time, this will be ideal. This has been explored at different levels in the approximate computing community with different results, because it's going to be harder to keep tracking what is the accuracy you're producing to then, let's say, match or configure whatever you're doing. In this case, let's say reconfiguring the logic, because there is going to be the overhead related to that, and not only in the reconfiguration, but in the estimation process. So this is still something open, let's say, in this way, how dynamically to adapt accuracy. But for sure, for now, what we have been thinking is we have an application, we want to map this application, especially in low-end FPGAs, those where we don't have too much resources. And be able, to squeeze as much as possible the application by introducing these approximations to actually feed it into some sort of these FPGAs. But considering something in between with configuration on the fly, it's something that we have been thinking about, not yet working on. But it's an interesting point to consider, especially on the type of applications. If you have some sort of classification one in general to change the model that you're using, and the accuracy that it has itself, this could be very interesting too.
Okay. Well, for the last one, we have been, taking too much of your time, but there is a last question. This is going to be a very, very easy one. It's done by Luis Duarte, who is an engineer here in Porto Alegre. He asked you, for energy efficient, is it better to use a dedicated design rather than an off-the-shelf circuit?
This is a good question. Yes, for sure. I mean, if you know your designs are going to change, dedicated one will be better. Sometimes you don't have the luxury, of hardware or designing your hardware or reconfiguring your hardware. That's why we have been looking also what is possible with off the shelf, whatever it's available in the market to play with. Uh, but this is just for that sector of possible platforms, devices that we could be using. But for sure, having a specific custom tailored design will be much better from energy perspective. Yes.
Okay. Well, since we have been already 70 minutes in the talk, I posted here in the channel also a GitHub project with where Guilherme Pain and my colleagues, my students developed with tools from AXLS is part of that framework where you can do cross-level exploration of approximate computing. I advise all of you interested in approximate computing to use that. It has contribution from many open source tools that you can use with a front end in Python and explore the effects of approximate hardware design, dedicated one, how that, let's say, impacts the C code level application execution of your application. So that's a very interesting work in which you have a collaboration between my group and also Jorge Castro and people from Germany in Karlsruhe and from other universities like Tech University of Munich and so on and so forth. So thank you very much for your talk here in the Rio Grande do Sul IEEE Circuits and System chapter. Thank you very much, Jorge. It's been a pleasure to entertain and be here with you. And for your last words, then please.
No, thank you very much, Sergio, Ricardo, all of you guys for the invitation. I'm always glad to talk to you, and I'm glad to to have the chance to present this. And for sure, anyone that is interested in some follow up, please feel free to Google my name, find my email, and drop me some lines. Thank you very much.
Thanks, Professor Jorge Castro-Godínez. With that, we finish the transmission. I wish all of you a good day, night, whatever you are. And thank you very much.